Hello, ladies and gentlemen. Welcome back. I hope everybody had a good break and used it to develop some connecting opportunities, to quote this year's AMTC title. Whether you stayed with us here for the breakout session and those great interviews by my colleague Sven Krause, or whether you enjoyed the networking tables during lunch, because of course, as we never tire of saying, it is in fact building that ecosystem and learning from one another that is what this forum is all about. Which is why, for the next hour and 15 minutes, we want to stay with our regional focus and continue looking at what we can learn from industries that are playing a leading role in developing innovative AM solutions and scaling up in their particular region. And we're now in Europe, both literally and figuratively. It is my pleasure to introduce the first of our outstanding presenters of Blueprint cases from Europe. We begin with a duo. Dr. Michael Ott is Head of Production Innovation Technology Center Mechatronics Products at Siemens Healthcare, Siemens Healthineers. And joining him is Max Horn, who is Group Leader Additive Manufacturing at the Research Institute Fraunhofer IGCV. Welcome, gentlemen. The floor is yours.
Thanks a lot for the kind introduction. Max and I would like you to take you on our journey in terms of to investigate the possibilities to produce a sustainable heat transfer device by additive manufacturing. By taking you on our journey, it's nothing we did on ourselves. As you see on the top of our slide, we had a bundle of different companies joining forces together to achieve what we will present in the next 30 minutes. First, I'd like to give you a short introduction on what Siemens Healthineers is all about. Siemens Healthineers is, as you might know, a medtech company providing different medical devices, and we are strongly committed to technology and innovation to achieve the best performance and providing the best solution for our customers and the patients in the end. But technology innovation is nothing we see as our purpose. Technology innovation is a method, a technology, a tool we use to achieve what our purpose is all about. And when I talk about purpose, we see ourselves as pioneer to pioneer breakthroughs in healthcare for everyone and everywhere. And therefore, additive manufacturing is a perfect fit for us to achieve advantages we couldn't achieve without, and to democratize the possibilities of our medical components and devices. How do we handle this? For us, collaboration is very mandatory, which means we as Siemens Healthineers have a core team and focus on identifying different use cases on the one hand side, and the other hand side, understanding what the technological benefits are, and try to combine the possibilities of technology on the one hand side with the use cases we have within Siemens Healthineers. It's nothing we can do on ourselves. We are integrated and grounded on a huge ecosystem within Siemens AG, the company core technology for additive manufacturing and materials, where we are part of. But also for us, equally important is it to have an ecosystem with external partners like the mentioned companies. And for this specific use case, we investigated within a working group the possibilities of green laser and how we could address our solution and problems and solve them. So the core is technology meets the application. Only when both come together, you will have an advantage you can take use of. And when we talk about the use case, for us, the heat exchanging device we picked, it's one heat exchanger we use within our X-ray tubes. Here's one exemplary medical device shown. And for us, the overall goal is to achieve cost innovation, which means on the one hand side, being cost competitive compared to traditional manufacturing technologies, and on the other hand side, being more innovative than what we are able to produce and achieve in terms of functionality with traditional manufacturing technologies. So we address different questions. How are we able to redefine, rethink a completely and more efficient design, and how are we able to bring it into action by combining different technologies in one holistic process chain? When we talk about additive manufacturing, for sure, in the core of the process chain is the AM process, but for us, it's much more. It's important to include all the possibilities and limitations of the pre-processes on the one hand side, but also the AM-specific post-processes. And it's not, let's say, complete with all these considerations. You also need to think about what is the traditional, what are the traditional manufacturing technologies you need to really be able to finalize a part which fulfills all the requirement needed for your application. And it's always the weakest member of the chain who defines what your limits are. It's not about only AM, it's about the combination of all the technologies. So when you talk about design for additive, it should also be designed for surface treatment or for post-processing. And the combination of all is rather complex, and the holistic process chain is the most important thing to consider when you think about additive manufacturing, which is why it's much more than only 3D printing. For us, to take in consideration that we only have some minutes to present, we picked three major process steps to give more insights. The first one is the AM data preparation. I think you all agree with me. The more complex the part is you are interested in, or the more complex the use case is you're interested in, the more high sophisticated simulation tools are very mandatory to achieve functional, optimized, and for this specific use case, very efficient heat exchanging components. And we picked one. We did optimize by simulation, and for us, as Siemens Healthineers, was placed to challenge the possibilities of additive manufacturing. As you can see, compared in the reference, which is the traditional heat exchanging and the optimized heat exchanger, we have some advantages. And the question for us would be, how can we actually answer these challenges with the right AM technologies?
Perfect. So thank you very much, Michael. The next challenge we had was the manufacturing. The component is a pure copper and copper alloy part. And as you all might know, copper has a high reflectivity of red lasers, which are commonly used in LPBF machines. So you either need very high energy inputs or need additives to increase absorptivity of the material. So we went for a green laser, which, like copper, has a much higher absorptivity of the green laser light, and it's said to have a larger process window and a more stable process. However, there aren't too many machines available on the market, so we had to start from the scratch, basically, and start with very basic investigations, trying to identify the weakest link in the process chain, as Michael said. Through primary investigations, we found that we have a very stable process and a large process window. You can see the sample parts in the back. With the standard process parameters, which were our starting point, we were able to achieve 99.7% density throughout all parts and 100% ISCS electric conductivity. And also we're already able to manufacture filigree structures with a large overhang, as you can see with the sun-shaped parts, for example. But we also identified some challenges, which are basically two. First of all, part resolution. The green laser has a 200 micron spot diameter, which is way larger than the structures we wanted to manufacture. So we had to overcome this challenge. And also, as you see at the image here, the physical properties of copper lead to drips, also known from welding. And we had to minimize those in order to manufacture the filigree structures. So by enhancing the process parameters, as you can see exemplary here, depicted by track width over the volumetric energy input, we were able to lower the minimum feature size below 200 microns. However, as you can see with the white spots, the drips scale along with it. So even though we were able to start from somewhere here to manufacture already quite filigree fins over there, we still needed the surface treatment. So this was one key takeaway there. The next weak link, so to say, in the process chain is the surface treatment. Then let me just show you a very rough excerpt or a brief excerpt of what we did there. On the very left side, you can see a small segment of the heat exchanger as built. So that's how it comes out of the process after process parameter optimization. And then we basically compared different post-processing surface finishing solutions that are actually able, and that's the challenge, to treat all these small fins in the part. So chemical etching was investigated, which is very hard to control at this level of precision that we needed. Plasma polishing is very promising in terms of surface smoothness. However, our part acted as a Faraday cage, which means the surface was treated very well, but the fins were not. So the then very promising process was the hertization, which is an electrochemical polishing process that yielded very good results. But again, the finding the right process parameters, even for this post-process, was very time-consuming and challenging. And that's basically the key takeaway or key message we want to say on this slide. The post-process chain and the definition of the post-process chain with all the process and the parameters took as much time to develop as the entire in-process did. So this must be considered when working with challenging parts like this. But eventually, we managed to manufacture it. Unfortunately, this is just the rendering, but we manufactured the part. Many of you might have seen it yesterday. We also have it with us. So come and approach me. I'm happy to show it to you. And we managed to manufacture those roughly 1,000 small fins that have a thickness of 135 to 150 microns. They're fully dense. They have an electric conductivity of 100% IACS. And this part is basically ready to put into operation by the Healthineers.
No. What are our key takeaways for us? None of us would have been able to make it alone, so it's all about collaboration, what you already have heard in the previous presentations. And in openness, connecting expertise with others is simply key. It's all about considering the complete process chain end to end, to think about what is your limiting factor and how can you maybe overcome the hurdles you have within the process chain? How can you shorten your process chain and what limitations are you faced with? It's all about not only thinking about functional optimized parts, but also about production ready design. So design for additive is one truth, but you have a lot of different technologies you need to consider. And it's all about going hand in hand, the different views of designing a new part. And for sure, it only is possible with increased complexity by using powerful simulation tools. And last but not least, what makes me very optimistic for the future is that the innovation leaps within the environment ecosystem are really large. Though even if, as you can see on the left hand of the slide, the cost situation is yet not the goal we'd like to achieve, it makes me very promising in terms of future productivity leaps in additive manufacturing ecosystem with new generations of machines to also achieve this goal. And then we would have a perfect match in terms of cost innovation by being cheaper than what we use currently, by being having a better performance. With having said that, I would thank you all for your attention, and questions I think will be at the end of all presentations. Thanks a lot.
Thank you very much. Thank you very much indeed. And some questions are already coming in, which is great, but we are going to go to those at the end of the session. So, dear audience, please do keep sending us your questions. That's wonderful. And the ones that I saw there are very specific indeed, so very helpful. We go now to a second duo of presenters. Hendrik Alfter is General Manager AM Europe at Oerlikon, and Kilian is R&D Manager for Additive Manufacturing of RF space components at Airbus Defence and Space. Great to have you with us. Please join me here on stage and take it away.
Yeah, thanks a lot for the introduction. Good afternoon, ladies and gentlemen. For me, it's a pleasure to speak here today with Hendrik about our success story. How we went from small parts, from small ALM manufactured parts, to a big cluster operating in space. I think it's important to understand the needs of space components, and that's the reason why we should have a closer look for upcoming requirements for a next generation of satellites. So in the past, main application for satellites or for commercial satellite applications was television. Many users want to have the same signal to the same time. Nowadays, the demands changed a little bit. Having a look to multicast, internet, 5G, 6G applications, there's a demand, or there's a need to share different information to different users at different times. And for us as a satellite manufacturer, this results in a high number of antennas on a satellite, and therefore we have a new challenge regarding mass and accommodation on that satellite. So, and in the end, it's a simple calculation. Our customers are asking for more spots, more capacity, flexibility, but the price shall be stable. And based on that requirement, we need to rethink and we need to think about our well-established processes, and decided to go into new and innovative technologies, and these were novel manufacturing techniques. Yeah, we started that cooperation around about 10 years ago. So we have a close cooperation with Oerlikon AM, and at the beginning, it was important that our design engineers talked to the ALM machine operator engineers, because they need exactly what we can and what the other company can. And yeah, it was essential to understand the needs and the boundaries of each other, especially because RF components are differing a little bit from other applications. For us, the geometry and the quality of the inner walls of that component is interesting, and this is essential for us. And mechanical strength, porosity, and so on, it's just a side condition. So let's have a look to the hardware. 10 years ago we started with that relatively simple screw waveguide. It seems to be really simple, and it is really simple by using ALM. But if you want to manufacture it with milling, for example, you cannot access it really, because you have a change in 3 directions. And with milling, for example, you need at least 2 or 3 single parts. However, with ALM, it was easy. It was a product where we thought, as okay, we can go on. And then we increased the complexity. We started to develop polarizers, what you can see here. We started to develop couplers and horns. And in 2018, we took us a heart and we thought, let's combine all features which are necessary on satellite. For example, you can see here at the bottom or right here in front of me. So we connected, in that case, I think 19 horns and 19 polarizers to one monolithic sample, including thermal and mechanical hardware. This was something what was not possible before. And This cluster was the beginning of our success integration of additive layer manufacturing in our processes, because all requirements I mentioned before, good IF performance, low mass, and lower costs were satisfied. So let's go to the next slide to give you some more information about these feed clusters. You can see at the top a typical feed cluster which will operate in space soon. And it was manufactured as a completely monolithic sample. So we have round about 100 horns, we have polarizers, filters, mechanical and thermal hardware. At the bottom, you can see an adequate part if we would use conventional machining, so milling. And there we need a lot of different structures and so on. By manufacturing such a component by conventional machining, lead time is round about 3 months. Then we need to integrate it, additional 2 months, we have to test it, additional 1 month. So we need at least 6 months before we can deliver such a component. With additive manufacturing and the other cluster, we gave it to our manufacturer, in that case to Oerlikon, and after 2 weeks we had it on our table. Of course, we need to test it, but I would say after 3 or 4 weeks we can deliver it. Because of the monolithic design, we can save time and money for integration, because we do not really have integration, especially if you have in mind for our business, for space business, there is no failure allowed. If a component is damaged in space, we cannot repair it. But for the conventional one, you can see at the bottom, we have round about 1,000 screws. Each screw has to be integrated, to be checked again, and to be signed. Another important point is the mass, which is 10 times lower for the ALM manufactured components. And if you have in mind that each extra kilogram on a satellite launch costs round about 10,000 euro, there's a big benefit for our customers. So far from my side. In that case, I will hand over to Hendrik.
Thank you, Michael. Yeah, honestly, I have to say I'm really proud to be here because I'm able to present you something which we talked the whole morning about it. So many months we are talking about applications. This is an application which is fortunately not any longer manufacturable with conventional manufacturing methods. This is a part which will be in future even produced by AM. And this is our future, to find exactly these kind of applications, to be really successful with AM. And that is the reason for this sentence, transforming customer requirements into solutions. This means we are really able now with AM to deliver these solutions about accuracy, about materials, high conductivity. All these topics are now covered. So that means we are not looking for the step into industrialization. We are already in this game. And we are now in the situation that we are finishing our journey regarding prototyping, development, and now at the next stage into serial production, which is a long journey. And I show you a few things which we did in between. So the full process capability, which was already announced and explained, is something which is really key. So additive is one part of this capability to go into to start this journey. It starts, of course, with the material and the selection of printers. So this sounds a little bit crazy, the selection of printers, because it's really essential to understand what the customer need is and to look for the right solution to print something. It's not only about dimension, it's a way the method is already established so that we can really start to work on something which is reliable. Sometimes it's really crazy because I met a lot of customers and they start to explain us which kind of machine we should use and which kind of material we should use. And then if you asked about why you asking us for that, why we should do that, then you get a lot of answers. And when you then start to please give us a specification about material, about certain process steps, then the discussion starts, because there are not so many specifications available, and we have to develop that. And this is the big success of our project, that we will start in the beginning to develop these specifications, and not only for the printer. So we came to a solution. Now it's a little bit tricky because we figured out that we need now two printer two printer types from two different companies for more or less the same application. And we had a good meeting this morning about cost reduction, about opportunities for the future, and it was a discussion about opportunities. And one is, of course, cost reduction. And I'm really happy to talk about cost reduction because always we are talking about development. What could we do next? What could we do better? But at the end, we are here with this industry, to gain benefit and profitability. And this is something which we have to do with the customer. And we have to explain authentically, transparent, where are the opportunities are. And this means in this kind of full process capability, transparency is key. The next step is post-processing. It was already mentioned, but we did so many discussions, so many tests with suppliers in post-processing to find the right method to gain the inner structures of this device. At the end, we are successful. And it shows already that we don't have to be the experts of this method for internal structures, but we have to understand the customer requirements. We have to be the interface between customer and technology experts to really get it to this solution. The last topic which I have to mention is the topic quality management, because quality management is something which is key. To show transparently what we did, even when we failed, that we know where we have to improve, and that we have a very well-managed process, documented everywhere, even to give direction to the people on the shop floor, to give direction to the customer regarding requirements, and that we really know what we are doing, even when we did something wrong. And there are a lot of tests which failed, which we now have to improve, and it's so important to be even fast and accurate to figure that out early. Some nice pictures about process steps. I'd like to show you this surface treatment, this chemical agent heatization. This was a key technology to understand how to get the surface structure inside right, which we did. And I'm very happy to say that after this very long journey, understanding this process, now we know how to improve. The other topic, a standard thing, I was not celebrating yesterday, it's just the flu. The topic CNC milling. This is with these kind of devices, and you showed, and Michael showed already the actual ones, we are really on the edge. This means we have to understand really how to do that, because if you put a printed part into a milling machine, and you have to understand that you have to put it sometimes more into the milling machine and then mill it precisely to the requirements, then you have to really understand this process. This does not mean that we will do this in future in serial production, but it's key for us to understand what we have to do in milling. Handling of these devices, you can imagine if you have to do the logistics for this device internally and externally, that you have to secure this part carefully, that it will not get damaged. So to figure out what kind of fixtures we have to use was the second key in this process, and I'm really happy that we can solve this as well. So last slide, we are talking about partnership, and we are talking about trust and to be authentic. And we were really able to do that. And I remember so well our start when we presented Airbus our project management system, and to show them correctly where we are, where we want to be. And we use this tool during the whole project to follow it in a common way, to understand where we are, where the issues are, where the problems are, the challenges, the benefits. And we keep this transparency ongoing through the whole process, and this is the outlook for the next year. Even for the serial production we are starting next year, we will continue with that. So, my wife said, I'm really proud to present that. I'm really proud to say, yes, there is an ongoing project next year, even the year after, and the journey continues. So, yeah, happy to present about the next challenges in the next AMTCs in the upcoming years. Thank you.
Hendrik and Michael, thank you so much. And I'm very glad that you left the part there because I'm dying to pick it up and test that mass that we just heard about. Let us now go to our third presentation in this session, which comes from Oliver Schieler. He is assistant to the head of development Exterieur at Audi. So we move on now to the automotive sector. And please, Oliver, the floor is yours.
Thank you. So, good afternoon. Unfortunately, as we heard, Dr. Mlekusch cannot join the conference today, so I have the honor to be here to represent him. My name is Oliver Schieler, and I will tell you something about the Audi way to use additive manufacturing today. More than just a gimmick, an AM blueprint for customer individualization. So, the Audi way consists of three main pillars. The first pillar in the product development process, the second pillar for our customers, and the third pillar for tooling. So, what does these buzzwords mean? I will explain it to you in the following slides. First, AM in the product development process. As you can see here, we have two different AM units at Audi, one for plastic, one for metal. But they not only produce parts, they offer engineering support, they offer manufacturing support, they lead the technology development at Audi. And as you can also see here on the right side, the volume increases year per year, and I'm quite sure that it will go on. The second or third pillar is the tooling. So we develop and manufacture a lot of different tools with additive manufacturing. We use them for the handling process, for manufacturing operations, for welding, but the most important application for us, for this technology, is the use for hot forming tools. But what are the benefits for us? The AM technology is the only technology, in our opinion, that enables to build up these cooling channels really close to the edge. That in turn leads to a significant reduction of the process time and increase of the tool life. The effect you can see on the thermal image here is that on the left side with a conventional insert, the temperature is really high, the risk for cracks is really high. But on the right side, as you can see here with the 3D printed insert, we can reduce the temperature, reduce the risk for cracks, and reach much better results in the parts. But now to the main part of the presentation today. When does AM generate a real benefit for us? We divided this question in two parts. The first part is when does AM generate a real benefit for Audi? First of all, it has to be a business case. We want to earn money. We are a company. For this reason, it has to be fully automated. The part development, the 3D printing, the manufacturing, and so on. And we are a design brand. Our customers buy our cars because of the design. For this reason, it has to fit in our design. And last, we should be able to homologate it. If the process or the part has an influence onto the consumption of your car, it has to be an influence on the homologation process. Oh, sorry, I was too fast. And now the benefit for the customer. Our customer wants a real benefit, not just a gimmick. And it has to be affordable. Also, he wants to individualize his car if he thinks about AM. One topic that most of the people doesn't think about is the experience. Our customer wants to have a real experience with AM. Based on these requirements, we thought about a meaningful application and we decided to develop a customizable rear spoiler mount, as you can see here. But how could this be a benefit? The design of the mount allows you to choose between top speed, cornering, or something in the middle. Perhaps some of you are interested in motorsport. There you can adapt the angle of your rear spoiler mount with some screws. But for the standard Audi customer, this isn't the solution. For this reason, we enable our customer to choose one setup in the configurator so he can configure his own setup. A little bit more top speed, you can adapt it in the configurator. But what will happen after the configuration? We developed an algorithm that designs, based on the customer's choice and the loads, fully automatic the part, as you can see here. But it's more than that. You all know that one of the main cost driver is the post-processing of the parts. We heard it in the last presentations. But or for example, also the demounting of the structure, the grinding of the connection points of the supporting structure. But our algorithm generates an inner structure in our mount of the rear spoiler that it's also a supporting structure. So we don't need external supporting structures. We don't have any processes, any post-processing where we have to demount the external supporting structures. We don't have to grind this part and we put it out of our 3D printer, we clean it and we can mount it onto our car. So the customer experience starts in the configurator where he can adapt the car concerning to his requirements. And the experience continues every day when he drives his car. So this is one example. We have hundreds of them with different configurations. We mounted the rear spoiler mounts on different cars. We installed the rear spoilers and drove these cars, and it works. And now again to the highlights of our project. It's an fully automatic generated organic lightweight structures that you see here. It has no external support structure. The process is fully automated. The configuration in the configurator by the customer, the design, and also the manufacturing. And it's also material independent. It's your choice if you want an aluminium rear spoiler mount or a titanium rear spoiler mount. We will generate or it will be generated automatically depending on the material parameters. So in my opinion, this is more than just a gimmick. It's a real benefit for our customers. But now we have to look again on our requirements. So as you can see here, we fulfill almost all of them. Unfortunately, it was not possible to homologate this product. We still have to homologate every car in hardware. And if we have to homologate every part with a new rear spoiler mount, it would be too expensive for our customers. Because we can measure the consumption of the car if we have another configuration of this mount. And now to the learnings. So for our customers, the production technology itself is not relevant, but the outcome of it. AM has to allow a perceptible benefit for the customers. The whole process chain has to be regarded in the development process. We also heard that. But our customers are design-oriented, but they want to be designers. So our customer don't want to design a new rooftop or something. They want a nice or a really good designed car, and they only want to change anything, optimize anything that generates for them a real benefit. And the last point, we have to keep the homologation process in mind. And now for the future, what is the Audi way of additive manufacturing in the future? What are we expecting? We expect in the product development process a constant increase of the produced volumes. For our customers, at the moment, we still expect that AM is a niche technology for specific individualizations with real customer benefits. And for tooling, here we estimate a really high potential for a new scale of die casting toolings. Yeah, that was my presentation. Thank you, and see you later.
Thank you very much, Oliver Schiele. And now for the final presentation in this session on Europe, we go to another duo, another pair. Sonja Wolfrum is Senior Key Expert in Additive Manufacturing at Siemens, and her colleague Markus Goehl is Head of Manufacturing at Siemens Digital Industry Automation in the Haguenau plant. So please join us on stage and get us started.
Yeah, thank you very much for this kind introduction, and welcome everybody to our presentation, Making AM Parts Available Anywhere and Anytime. Yeah, we always talk about these great fancy structures that can be produced by additive manufacturing, but what is often underestimated is the use of additive manufacturing in factories to produce parts for their own needs. These parts include manufacturing aids, jigs and fixtures, and spare parts, or even special applications such as grippers for robots. So in our presentation, we want to give you some insights in our factories, how we use additive manufacturing to increase our productivities of the factories. And besides that, we want to show you our approach at Siemens, how we transform an organization with more than 300,000 employees towards leveraging additive manufacturing for its own use. So here you see the different businesses we focus at Siemens. As we already heard from Michael Ott, at Siemens Healthineers we produce medical devices. Siemens Mobility, we build trains. Smart infrastructures, we offer services, solutions, and products, for instance, for smart buildings or smart power distributions. And at Digital Industries, we produce industrial automation and also support our customers in terms of their digital transformation. But now let's have a closer look on our factories at Digital Industries. So we have 30 factories globally distributed, and now we want to build an additive manufacturing network across all 30 global production sites to make AM parts available anywhere and anytime. So what are our 4 most important ingredients to do that? First of all, we set up or installed Center of Competence, local and globally at all Siemens businesses, where we have additive manufacturing experts and also industrial AM machines. And across Siemens, we have more than 200 industrial additive manufacturing machines Then second is to install or to have a local ambassador in each factory. And for sure, very important is the management commitment and the support. And fourth point, number 4 is to have the right tools to make AM parts available as easy as possible. But now let's ask our factory head of our Siemens Digital Industry factory in Haguenau how they use additive manufacturing and how they increase their productivity of the factory by additive manufacturing.
Thanks, Sonja. Some words at the beginning on the factory. So the factory is located in northern Alsace, which is also industrial powerhouse of France. We have about 800 employees there and produce 400,000 products. And we are characterized by low volume, high variance products. And like every factory, we have started 6-7 years ago with 3D printing. We established a center of competence, centralized, had some expensive investments, and then we tried that we utilize this to our maximum of the capacity. One side effect is this: if you maximize the utilization, you don't optimize the lead time. So beginning of 2021, some of the younger engineers contacted me and said, wouldn't that be possible that we have 3D printers close to us, close in the production departments, so that we can be faster? So after some discussions and some trials, so we said, okay, let's put in all of our 4 operational departments, being the 3 production departments and 1 logistics and quality department, we put in the printers. And what I'd like to show you now is the effect this had on the organization or the way the work changed. So I have a little example here I brought to you, and this is really not about the technology. I think you have seen excellent examples of technology, but this is of the way how the work changed, how people changed the behavior in working. So on the left side, you see this milled tool. It's a little tool which we use to calibrate our flow sensors, our ultrasonic flow sensors. There's a laser inside, and then you need to calibrate this. So this tool was in use for years, was not so accurate, but somehow people worked around this. When we introduced the 3D printers, after a couple of days, they started to work on this, and then the next point, the little blue one, you saw this version. And it was just a copy, but more accurate, so you did not have to do this fiddling around. But when they went on the shop floor to try it, they figured out, it's still too short. So the same day, they just printed a longer version, went down to the shop floor, and this worked quite well. Until they encountered again some problems with some variants where the accuracy was not good enough. Again, they thought, what could we do? And their solution was finally, they imprinted some screws. And this whole process, just having these fast feedback loops from production, what does work, what does not work, this is what I think is so fascinating about the possibilities when you unleash 3D printing into the organization. And now after having this introduced for 1 year and having this run in several departments, what were the learnings? What were the effects? The first one I just mentioned, this is really these fast trials, fail fast, learn fast. There is no big efforts. You don't need to put in some big administrative forms to do the next improvement loop. This is just, it increases really the speed for improvement. Yeah? And this is what we need in a factory. We want to have fast improvement because productivity is our daily bread and our daily goal. The second effect was, because we entered the 3D printers in the organization, this created a lot of intrinsic motivations that people started to use them. They started to do in a self-learning how to use the design programs. Yeah, so the community increased. So we went up from 4 experts 1 year ago, now to over 30 people. And this is just the people doing the printing. There's other people inspired for ideas, but more on this later. Fast solutions, as you have seen also, uncovers old problems. I have never heard, honestly, from this little problem that was shown, but it was a problem, and then the team was able to fix this on their own. And this, I think, is really great. And with this, they found new problems, which the bigger problems just covered. And then for the ones amongst you who are familiar with Lean, there's the 7 ways of Lean. And there's an 8th one, if you don't use your creativity of your staff. And with this approach, we triggered the creativity of the whole staff. Now, operators are very encouraged by bringing the problems to the engineers and then say, this is a problem, this is really bothering me, what could we do about this? They sometimes come already with a little sketch that, maybe we can do it like this. The next day, the engineer comes, has a solution. Maybe it's not the perfect one, but it's better than the situation before. And this brings me to the last point, that this creates also the motivation in the whole staff across all levels in the factory. Because everybody likes to solve problems, whether these are the operators in the line, whether these are the people in the engineering offices. Everybody likes to find solution, everybody likes to work on solution, and everybody wants also to see that you have an impact on this solution. And with this is our experience in the factory, this really unleashes a big potential. It's not the high tech, but it's really this dynamic, this speed, this scaling up, which is so fascinating for me, and this creativity that we can see now in the factory. So we will definitely continue printing and training people to do this, because I think we have just scratched the surface on the possibilities here.
Yeah, thank you very much, Markus, for giving us these insights in your factory. This brings me now again to my list of the 4 ingredients to build our additive manufacturing network within Siemens. So number 4 is you need to have the right tools to make AM parts available as easy as possible. So at Siemens, we use the Additive Manufacturing Network. This is a digital platform that is also commercially available. And with this platform, we connect our internal consumers on the one side. That could be employees who want to purchase a part. And on the other side, we have the internal providers. This could be either our local or global competence centers, or even available printer capacities in our factories. And furthermore, external suppliers, so service providers that are qualified, in our case also for Siemens, and that the internal consumers can purchase parts from both, from internal providers and also external providers. So here on this slide, you see the whole entire workflow for the end-to-end order-to-delivery process with the different steps, starting with the order and delivery. So with our digital platform, Additive Manufacturing Network, all steps are available on this platform, and we realized an integration to our CAD/CAM tool and furthermore also to our manufacturing execution system. And what is very important, and this you can see on the top right, is that you integrate such a platform also to your supply chain management tools, which means that you have a direct connection to your ERP systems of your enterprise. And this enables you to have an efficient ordering and also billing process. So to share our best practices and also to scale among the factories, we use the Additive Manufacturing Schaukasten or display case, if we want to translate it. Here our AM users have the chance to upload their parts, to define the technology that they were using, the material, and also to share their experience by using additive manufacturing. What kind of effect has it on the cost? What kind of effect has it on the time to product? And on the other side, the consumers, so employees who want to purchase parts, they can also use this AM Schaukasten to look for files for certain parts, and finally to get the experience from our AM experts. So this helps us to scale, another tool to scale among our factories. Bringing me to my last slide. So in terms of transformation, an organization with more than 300,000 people towards leveraging additive manufacturing for its own use, you can see here that we formed our network of network. So in the center, the network of printer capacities in factory, then also the capacities of printers cross-factory, connected also to our global and local competence centers, and even to the 150 external certified suppliers. So these are our tools, is our approach to make additive manufacturing parts available anywhere and anytime. And we would like to thank you for your time and for your attention.
Thank you so much, Sonja and Mlekusch. If you would just please take the last two seats here on the stage, and if our other speakers would now join us, then we can take some of the audience questions that have been flowing in. And I'll ask you to sit in the same order in which you presented. So that means that you, Oliver, you would be prior. Yeah, exactly. Yep. Perfect. I have some specific questions. Some audience members have designated to whom they should go. Others have not, and they got a bit mixed up since likes push some of them up, but others not. So if I ask you questions like whether your part included copper or not, that has something to do with the fact that the questions are now mixed. But I'm not going to start with that one. I will start with one that essentially would go to all of you, I think, but I'm just going to ask whoever wishes to speak to it to give me a sign. The question is this: how does the AM industry deal with conflict of opposition or a conflict of goals between the perspective of being sustainable and being profitable? So sustainability versus profit. Anybody want to talk about that? Sure, please.
I think there is no, it's not an opposite. Sustainability means economic, environmental, as well as social, reasonable. And in terms of economic reasons, for sure it is important, but it's not only about the part costs itself, it's about taking the complete life cycle into consideration, and so it's included, it's not an opposite point of view.
Thank you very much. Anybody else want to weigh in on that point?
Maybe
Go ahead.
Just to add a little part on that. Additive manufacturing is comparatively small to the overall manufacturing market still, but it scales very fast. So I think this is now the right time to address the challenges. So the ecologic and sustainability issues that we might have don't scale with the market. So I think if we address them right now, this is the time to do it.
Thank you, and those are helpful impulses for our discussion later on, where we'll focus entirely on sustainability. I have a question here. I'm basically going by likes. So I have a much liked question for Audi, which is this. How was the presented part printed without support structures? Was a local process parameter adaptation applied?
Sorry, could you please
Okay,
repeat
here we
it?
go again. How was the part that you presented printed without support structures?
Oh, okay.
Was a local process parameter adaptation applied?
Yes. Yes, it was printed without support structures. We have a special parameter set up, especially for this structure. And as I told you, it helped that we print a very complex inner structure, and this inner structure supports the whole part. And for this reason, we don't need any outer structures.
Thank you. Then I have a question to Airbus and Oerlikon. What are process definitions and specification descriptions based on publicly available standards?
That's a good question. Publicly available standards. I think, let me phrase it differently. With this project, we really start the journey to be aerospace ready. This means the standards which we are following up, these are standards which of course are officially available, and we have to do that because it should be no secret anymore in these kind of steps. So from this point of view, yes, we are dealing and we preparing ourselves, our production, exactly to these kind of standards which are officially available.
Thank you very much. Now, question Siemens copper printing is this question. Is there an interest in decreasing wall width and spacing between wall dimensions?
Then increasing?
Do you see digital, sorry, that's bringing around, excuse me. Is there an interest in decreasing wall width and spacing between wall dimensions?
I try to get a question and try to answer it. So our major goal was to have a minimum wall thickness as thin as possible. So there's no differentiation between the walls outside and of the fin structure. And the main goal for us was to have minimal wall thickness in terms of reduce pressure drop, which is one of the most important which was one of the most important topics to optimize the heat exchanging device, and thereby it being optimized of the liquid flow through the heat exchanger. So there is no change in wall thickness.
Okay. Then I have the question that I mentioned. Why did you use copper and not aluminum?
Copper because the current heat exchanger also is based on copper, and we are not fixed to copper. So if another material provides similar properties, copper has, I would say, higher heat conduction properties than aluminium. It would mean that we would have to completely redesign and having new, let's say, outer box boundary conditions we wouldn't have within our application. So we would rather be more interested in having materials with a better heat conduction than less. So being better than copper would be good, but I think there are some limitations in terms of materials.
Thank you very much. And now I'm not quite sure. This one is also to Siemens, but it came in late, and I think it may be to you. But if it's not, just let me know, and we'll go back to the colleagues. Do you see digital thread software, e.g., in your AM network, as a support for existing AM users, or as something that could trigger a sea change in broader AM implementation?
Sorry, what was the last part?
Yeah, I'm going to just tell the audience, we have some very hard to understand audio effects up here. We've got a lot of echo, so if you're surprised, I think that is one of the reasons we're having some communication issues. Do you, okay, here we go. Do you see digital thread software as a support for existing AM users, or something that can trigger a sea change in broader AM implementations?
The sea change?
A major change.
Okay, yeah, good question. So let me think about it. So digital thread software to support the AM users. Yes, that's always a very important case. And then the second part of the question was?
Basically asking you whether, the question has now disappeared from my screen, but basically asking you whether that will trigger a major change in the way that you're applying this.
Yeah, sure. I mean, at the end, it's always software applications are very important, not only for additive manufacturing, but for any technology that you're using. And for sure, in the field of additive manufacturing, we are just at the beginning, and this will be improved in future times, all the software tools, and then also supports the AM users.
Thank you. Then I have a question. I'm not sure if this was intended for one specific group or for everybody, so I'll just ask you to raise your hand if you would like to answer it. Are you making use of computer tomography to evaluate the quality of the AM parts that you produce? Anybody? Yeah, Hendrik?
For sure. Also, computer tomography is key. unfortunately, because it's quite expensive, and we have so many other opportunities to show that we are producing proper parts with AM. And I think it's a big threat to the whole business, because we have to replace this technology to show that we can do it differently, and we can show that these are proper parts. I think, what do you think about?
Yeah, it's absolutely correct. So it's a really expensive step, and at least so for our antenna components I showed you today, it's important to have a good quality also in the inside, but especially for the antennas, I mentioned it during my presentation, mechanical strength, porosity is not the major topic.
Thank you very much. And then one more question for the first Siemens team. Which beam profile is used for the green laser? Probably Gauss?
You're closer to the answer.
We're really sharing best practices here.
I've been schooled on this, and I might hand the discussion over, or address the discussion to the Trumpf. I thought it was Gauss, but due to it being a disc laser, it has a very flat top, but it's not a flat head. That's what I learned. But maybe Trumpf can share some information maybe later.
Yeah, if you are interested in that very specific answer, dear audience, and you are with us here in the room, then maybe during the break you can catch up with Max, and he will bring you to the Trumpf colleague who maybe would know. And if you're online, perhaps you would send that question to us, or we'll try to get an answer to you one way or another. Now let me just ask, are there live questions in the room? Would someone in the room like to pose a question via microphone? Okay, could we go to Sven with the mic? There we go.
Very impressive example. Thank you for that. Question to the team of Fraunhofer and Siemens Healthineers. The iterations you did for the post-processing, we see a lot of development for simulation of the printing process. What is your view, how far we have developed on simulating the post-processing?
You go first.
Thank you very much for the questions, Sven. We did not use simulation of post-processing efforts due to the complexity of the part. We were just this was an ambidextrous approach already, where we tried to explore the in-process while exploiting all the potential and bring it to the part. And the same goes for the post-processing. To my knowledge, simulation of post-processing for parts like this have not reached the technology readiness level that we would need for this level of complexity, I think. But maybe you can add on that, Michael.
So in the specific use case, or in taking the powder bed fusion process we had before in the post-processing, I think it's hard to take the topology of the surface into consideration, how your post-process will actually perform, which might really be a challenge. I have yet not seen a solution available in the market. In terms of other post-processing technologies, like maybe smoothing of surfaces in polymers, I think we are closer to a simulation solution, but for our complexity, I think there are some years to come before we would see a solution. But it might be a scientific goal to go for it and find a solution. Yeah.
Good idea.
Maybe I can squeeze in one last question. Unless other questions in the room, please hand up if you have another question. Then I would like to squeeze in one last question to Markus and Sonja, because I was quite fascinated by, maybe this is because I'm a generalist, but by the idea that putting these printers close to the workers triggered a new form of innovation and work process. And can you just say a little bit more about that? Is it because of the speed? Is it because of the decentralization, or both?
It is because of the speed. Everybody, let's say, you have an idea and then you want to have the proof of it. And this is how this whole thing works. And also we did We just put the printers in there. We didn't even train the people in the design programming. But what happens now is they start to teach them themselves because they see some other people are creating wonderful ideas, old problems are solved, and this creates this avalanche. And this is maybe also one thing. I had an exchange with some of the colleagues here, so I followed the advice you gave to do the networking. And everybody has a problem for finding parts for series production. And maybe this is because from the design ideas, this is still done in the old-fashioned way. But when you start getting more people involved, thinking in 3D solutions, maybe you have more people, and starting early. This was triggered by some young engineers just from university. Maybe this changes the whole thing to solve certain problems. You don't think in how to mill, how to drill this, but you think, how can I print this?
And I think this is a very
interesting experience that we made. Yeah.
Thank you very much. Fascinating examples from all of you. Greatly appreciated for sharing these wonderful blueprint cases that I think really tell us a lot about the potential and about how you're dealing with challenges. Let's give them a very warm round of applause, please.